Welcome to the deep dive. Today we're looking at a scientific paper you shared with us. It explores these non-local connections, these sort of spooky links between three massless spin 12 particles.
That's it. They originate from the decay of a heavier, massive particle.
And our mission really is to unpack what these non-local correlations mean for quantum mechanics, for our basic understanding of physics, but, without drowning you in technical terms.
We want to focus on the core insights and some of the surprising parts that come out of this research paper, which analyzes these three-body particle decays.
Let's begin with quantum entanglement. It's fundamental to all of this.
It is. Think of it like particles becoming linked, their fates intertwined no matter how far apart they get.
So if you measure something about one particle, you instantly know something about the others it's linked with, even across vast distances.
Which really clashes with our everyday intuition, what physicists call local realism.
Local realism being the idea that, well, objects have definite properties independent of being measured, and crucially, influences can't travel faster than light.
Exactly. And John Bell gave us a way to actually test this.
He developed Bell-type inequalities, mathematical tools, essentially.
Tools that set a boundary. They define the maximum correlation you could expect if local realism holds true.
And experiments.
They've shown again and again that quantum systems violate these inequalities, like a CHSH inequality for two-particle systems.
CHSH standing for Clauser, Horn, Shimoni, and Holt.
And its violation is strong evidence for quantum non-locality. It tells us those classical ideas of local realism are, well, incomplete.
Now, going from two particles to three or more, that complicates things.
It does. The landscape of entanglement, multipartite entanglement, becomes much richer. It's not just fundamentally interesting, it's key for future quantum technologies.
People are actually seeing this.
Yes, even at places like the Large Hadron Collider, the LHC. Recent measurements found entanglement and spin correlations between top quark-antiquark pairs. High energy stuff.
So why study this in particle physics specifically?
Well, several reasons. It lets us probe the standard model, our best theory of particles. It tests quantum mechanics at really high energies, where maybe gravity starts to, modify things.
And maybe gain new perspectives on quantum field theory itself.
Precisely. But most work has been on two particles. This deep dive focuses on three-particle systems, which are, relatively speaking, less explored in this context.
Okay, so the specific scenario in the paper
Is the decay of a massive fermion. Think of it as a fundamental particle, like an electron, but heavier into three massless spin 12 particles.
Why this setup?
It's a good test bed. It's complex enough to show interesting three-way entanglement and non-locality, but still theoretically manageable. And it relates to things we might actually observe in experiments.
And the analysis uses a framework based on what's called general four-fermion interactions.
Yes, to look at the correlations. We're focusing here on the non-locality aspect, building on previous work that already established entanglement in this kind of decay.
The goal, then, is to quantify these non-local correlations.
And to find out under which conditions, like decay angles, particle energies, the deviation from local realism is, well, strongest.
You mentioned different types of non-locality for three particles.
That's right. And different Bell inequalities test for them. The simplest assumption is what we call fully local real theories, or FLR.
Meaning no non-local correlations at all, everything independent.
Essentially, yes.
Yeah.
The probability distribution for measurements just factors completely. Each particle is its own thing.
And the Mermin inequality tests this.
It does. It sets a bound, let's say a value of 2, for a specific combination of measurements under FLR. Quantum mechanics predicts results that can go beyond this, up to a value of 4. Violating the FLR bound of 2 tells you the system isn't fully local real.
Then there are bipartite local real theories, BLR. What's different there?
BLR is less restrictive. It allows two of the particles to be non-locally correlated, like an entangled pair, but assumes this pair is completely separate, or local, relative to the third particle.
So some non-locality, but not full three-way connection.
Kind of. Two particles can have their spooky link, but the third one is outside that link.
And the Svetlichny inequality tests this.
It does. Its bound is higher, let's say 4 under BLR assumptions. Quantum mechanics can violate this too, reaching up to 4 times the square root of 2.
So violating the Svetlichny inequality points to something more profound.
It suggests genuine three-partite non-locality, a type of connection that involves all three particles together in a non-local way, something that can't be explained by just pairwise correlations.
You also mentioned a tight 4 by 4 by 2 inequality.
Yes, that's another test, specifically designed to be more sensitive to any deviation from FLR theories compared to the Mermin inequality. If a system isn't FLR, this inequality should pick it up. Its bound is 4 for FLR, while quantum mechanics allows up to 8.
How do entanglement and non-locality relate here? Do you need one for the other?
You definitely need entanglement for non-locality. If particles are separable, meaning not entangled, they can't violate any Bell inequality based on local realism. So Bell non-local states are always a subset of entangled states.
But is all entanglement non-local?
For two particles in a pure quantum state, yes. Any entanglement violates the CHSH inequality. But for three particles, it's trickier.
You need a specific kind of entanglement for this Svetlichny violation.
That's the idea. You generally need what's called genuine tripartite entanglement, a three-way entanglement, to violate Svetlichny's inequality and demonstrate that genuine three-way non-locality.
Let's talk about the interactions mentioned in the paper scalar, vector, tensor. These are types of fundamental forces governing the decay.
In this theoretical model, yes. They represent different ways the four fermions can interact during the decay process, and they lead to different outcomes for entanglement and non-locality.
Take the scalar interaction first.
With a scalar interaction, the final state of the three particles is what's called biseparable. Particle A, say, is completely separate from particles B and C, which themselves form a maximally entangled pair.
So no three-way entanglement.
Correct. Measures of three-way entanglement like the three-tangle are 0. In this case, the Mermin and the tight 4 by 4 by 2 inequalities can be violated, showing it's not FLR.
But not the Svetlichny inequality.
It doesn't violate the Svetlichny BLR bound. It reaches the bound, but doesn't go past it, consistent with the lack of genuine three-way non-locality.
What about the vector interaction?
That generally leads to genuine tripartite entanglement. It's more complex. You might find that A isn't directly entangled with B or C individually, but it is entangled with the combined BC system.
Indicating a true three-way connection.
Yes, and how much entanglement and how strongly the Bell inequalities are violated depends quite sensitively on the initial spin direction of the decaying particle and the geometry, the angles of the decay.
Are there clear patterns?
The paper shows plots. It's quite intricate. Some measures are constant, others have peaks and dips. The tight 4 by 4 by 2 inequality seems to be violated quite consistently for the vector case.
Even when Mermin isn't.
Sometimes, yes. And the Svetlichny inequality, the test for genuine three-way non-locality, is sometimes violated, sometimes not, depending on the specifics.
Finally, the tensor interaction.
The tensor case is interesting because the resulting state can actually interpolate between a completely separable state, no entanglement, and the maximally entangled three-particle state, the GHZ state.
GHZ for Greenberger, Horn, and Zeilinger.
That's the one. In the tensor case, direct pairwise entanglement might be 0, but the three-way correlations can be very strong. The Mermin inequality can even reach its absolute quantum maximum for 4 in some configurations.
But again, sometimes Mermin isn't violated.
Yes, and again, the tight 4 by 4 by 2 inequality might still be violated in those cases, showing its sensitivity.
And Svetlichny.
The Svetlichny bound can be violated with a tensor interaction, especially when the measure of three-way entanglement is high.
Is there a way to guarantee maximum violation?
For certain initial spin directions of the decaying particle, like if it's spinning purely along the axis in their setup, the final state becomes exactly the GHZ state.
And
then you get maximal three-way entanglement, and you see the maximum possible quantum violations for Mermin, Svetlichny, and the tight 4 by 4 by 2 inequalities, regardless of the decay angles.
So wrapping this part up, three-body decays are a natural source of multipartite entanglement and non-locality.
Definitely. And the specific type of interaction, the fundamental force involved, plus the kinematics, the energies and directions, really dictate the type and strength of these quantum correlations.
We also learned that different Bell tests have different strengths. They probe different aspects of non-locality.
Yes, that's a key takeaway. One surprising thing is perhaps seeing non-locality confirmed by one test, like the tight 4 by 4 by 2, even when another, like Mermin, shows no violation.
It really underlines the need for using multiple probes.
It does. Another interesting point is the connection between the initial particle's spin and the quantum correlations of its daughters.
And the fact that quantum mechanics sometimes pushes right up against its theoretical limits in these scenarios.
That's quite remarkable, suggesting these decays are, in a way, optimal systems for observing these extreme quantum effects.
For you, the listener, this exploration gives a peek into the fundamental weirdness and interconnectedness of the quantum world. understanding this isn't just academic.
No, it's vital for pushing the boundaries of fundamental theory and for developing the quantum technologies of the future, which will need to harness precisely these kinds of correlations.
So here's a final thought to leave you with. Since these non-local correlations pop up naturally in particle decays,
Could studying them in detail at colliders at these high energies give us a completely new angle on the nature of space, time, maybe even causality at the quantum level?
what other unexpected quantum phenomena might still be hiding in the results of these energetic collisions, just waiting for us to find them?